So my name is Katja. I'm IoT Specialist Solutions Architect. Have been with the company since 2019, but IoT is so cool, so I decided to switch over to IoT beginning of this year. I'm joined by two amazing people today. First is Mike, who is General Manager in the automotive space at AWS. And very exciting as well, we have a company that you might have heard of. So Mercedes is joining us with the Chief Architect, Kevin, to tell you about the exciting story to connect vehicles using AWS. Before we dive into the topic, how to build connected vehicle platforms on AWS, I want to take a step back and talk to you about scale. So in 2020, a level 1 vehicle model might produce up to 1 gigabytes of data per hour. We're going a step further, 2022, we're talking about already level 2 plus vehicle models, which generate more than 1 terabytes of data per hour. Looking at the whole market of 100 million vehicles per year, that might be driving around 4 hours per day, 300 days a year, we're going up to 120 zettabytes of data. That's massive scale. But we don't end in 2022, so let's go further. In 2030, a level 3 plus vehicle model will produce more than 10 terabytes of data in a single hour. Multiplying the 120 zettabytes we had before with 10, we end up with 1.2 yottabytes of data in total. So there's no compression algorithm for experience. So AWS, since day one, has built scalable platforms and services. And we want to talk to you today about which of these you can actually leverage to focus on your benefits and leave the heavy lifting to us. Before we can actually dive into how and what to build, let's start with the challenges and the opportunities. So first of all, instrumenting the physical world takes time. So there is a need for organizations to automate vehicle onboarding and testing. Second would be that future vehicle models, as we just heard, will generate multiple terabytes of data per hour. So we need better tools to discover and collect high-volume data. Last but not least, with massive scale comes more responsibility. So let's earn customer trust with robustness, which would be high availability, security, as well as privacy. Let's look at how this architecture for a connected vehicle platform might look like. We start at the very bottom with the device layer, which is about functions for hardware abstraction, the operating system, as well as device onboarding and management. It's the very foundation. On top, we have the connectivity layer, which concerns itself with the connection, the secure connection between vehicle and cloud, using protocols like MQTT or HTTPS. Between vehicle and cloud, we have two abstraction layers, which are software and data abstraction, which should provide a unified view of software and data afterwards. In the cloud, we have the operations layer, which is about monitoring, performing customer support, as well as managing deployments. And then last but not least, the one layer that differentiates your product and your business is the applications layer. And we at AWS recommend customers to leave the undifferentiated heavy lifting to AWS. So everything from device layer up to operations layer is something that we can help you with to focus on the level that, or give you the opportunity to focus on the level that differentiates your business. Because of the time we have today, we're going to pick a few of these areas and dive deep and show you how that can be done. So we're talking about device layer, connectivity layer, as well as data abstraction. In a little more detail, that means that I'm going to talk today or start with connected vehicle device management. So we are leveraging AWS cloud services to issue and register certificates for secure communication from vehicle over, from the vehicle gateway over to AWS IoT Core. Second is Connected Vehicle Device Defender. So we're leveraging a service called AWS IoT Device Defender to detect revoked certificates as well as certificates that are about to expire and perform rotation of those certificates in an automated way using AWS IoT Managed Services. Last but not least, we launched MQTT 5 for AWS IoT Core just a few days ago. And this is so exciting news that we want to share it today and dive into accelerating and optimizing the communication between vehicle and cloud with you in this session today. So as I said, we're starting with securing ECU communication. This is the very foundation. We saw that before. We have the device layer, which builds the foundation for everything when it comes to the connected vehicle platform, as well as us considering that we have a market of 100 million vehicles per year. So this is something that actually has to happen at scale. We're going to look at the architecture for this now. So you see on the left, we have the vehicle itself with a vehicle gateway which manages the communication from vehicle to cloud. We have an attestation, so a long-lived certificate on the vehicle itself already, and are using SDKs, so an AWS IoT SDK or a third-party SDK for the communication over to cloud. On premises, we have a root, like a trust anchor, that we want to leverage for issuing a subordinate CA within the cloud using the service AWS Private CA. And we have AWS IoT Core, where we need to import the certificate of the subordinate CA for the later flow for issuing and registering the certificate. This one is also going to include the just-in-time registration flow we have in AWS IoT Core, which is, when we talk to OEMs, the flow we usually land up with when it comes to a best practice for device provisioning. Oops. So the next step we're going to go is, first of all, we want to have the operational certificate we use for the mutual TLS communication on the vehicle. Two options. We might do or have the option to send over a CSR, so do use a client-generated private key to issue the CSR, send it over to an interface we have on premises, so a certificate broker, which then communicates with the subordinate CA to issue the certificate and get it back over a secure channel you have to have established before to the vehicle itself. A more batch-oriented approach would be the server-generated private key. So you can issue multiple certificates using the same interface with AWS Private CA and communicate those back to vehicle also over a channel that is secured. When we store the operational certificate, the vehicle gateway should check for the authenticity as well as the integrity of the certificate before. We're then going to use the certificate to connect over to AWS IoT Core and kick off this just-in-time flow I mentioned before, the best practice to register the certificate because it has been signed by the subordinate CA before, and then trigger a Lambda function, which then does custom testing if you want to check with a database or something else to make sure everything is valid, and then create the resources of an IoT thing, an IoT policy, which is a fine granular policy for your vehicle, what it actually can do in AWS IoT, and activate the certificate. Once we have a certificate, we're not done, because in the automotive space, it seldomly is the case that the automotive car, like a car owner, actually owns the vehicle from manufacturing time till end of life. Often, people own cars for about 6 years, so we actually need the opportunity to rotate certificates, also for the end of life, of course, if we want to revoke certificates after that. So that's what we're going to look at. We're going to use AWS IoT Device Defender, which gives us the option to use automated audit checks, which look, first of all, one of those checks could be looking for revoked certificate or certificates that are about to expire within the next 30 days or have expired. Also, with this AWS IoT Device Defender, we offer mitigation actions out of the box. First of those would be deactivating the certificate, which would make sense if the CRL actually had a positive result for the certificate being on there. And second would be publishing the finding to SNS, so our notification service, invoking a Lambda function, which then uses AWS IoT jobs, which make it easy for you to create and register a new certificate and then deactivating the old one. Also, there might be the case that your operational certificate was valid for a certain period of time, but your vehicle actually was switched off longer, so you don't have a valid operational certificate anymore. In this case, you still have the attestation certificate here that you can leverage to go back to the first flow we saw before to restart the communication with the certificate broker and get a valid operational certificate again, just as a plan B. As I said, we launched MQTT 5. I think we have all been waiting for this, so this is really, really exciting news. And while it's suited for many markets, the automotive industry has embraced MQTT 5 as its new standard for connected vehicle platforms. The ease of implementation, enhanced security, as well as the ability to deliver large amounts of data with a simple publish and subscribe method have enabled MQTT 5 to surpass older technologies like HTTP or SMS. We're going to look at 3 of the features. So we're selective here again. 3 of the features, because of time, we're looking at shared subscriptions, we're looking at request response, as well as the header fields that add benefit to your connected vehicle platform. First of all, for shared subscriptions, so that's what we're going to start with. Imagine, you might have one, but if you don't, imagine you have a huge fleet of vehicles connected. And those vehicle fleet, or that vehicle fleet with a lot of vehicles, they publish similar messages requesting configuration or publishing status updates. Now, before we launched MQTT 5, you could publish all of these messages to one topic and have one subscriber that actually listens in and works on those messages. But we talked about scale before, so now you can actually publish those to a shared subscription topic, which has multiple subscribers to listening to the incoming messages. This means we're going to load balance the messages for you, so only one of the receivers will actually, or subscribers, will actually receive the message. Which also means that in case something is wrong with one of your backend services, you can actually take that one offline. You still have multiple alternatives as receivers for the message, and your vehicle isn't influenced by a failing backend. So that's shared subscriptions. Second, we want to look at request response. So if we look at this request response pattern, Today, there's no simple way of getting positive acknowledgements back from the vehicle that you told it that something should happen and it actually has happened. So it received a command and it executed it. Now we have, with MQTT 5, the option to specify a response topic. So you send from, in this case, a Lambda function, the message to a topic and have the vehicle receive the message. And then on completion of the command that it receives, it goes back to the response topic with a success message. Just a note here, in case you want to have this combined or want to have something for your commands that's more stateful, look at the service called AWS IoT Device Shadows. Last topic I want to cover with you today is optimizing message routing. So the rules engine in IoT out of the box supports JSON, which allows you to make full use of the rules engine and specify when you want to route a message to which destination. In case we have a message like this, which is protobuf encoded, we actually can't make full use of the rules engine because protobuf isn't natively supported. Same problem if you send a compressed message where you can't inspect the message in the rules engine. Now with the header fields, you can actually determine in the information you get additionally to the payload where you want to store a message. We're looking at two flows here for a short example. First of all, you store a message in a data lake. And second, you also have a protobuf decoder, which should receive a message if it's protobuf. And then we republish to a topic and also store it in a data lake. I'm giving you an example query here to show you the benefit now, is that you can take from the header content type in this case, as well as format indicator, which allow you to see that the message actually is protobuf. And instead of sending it to the same destination, to the same backend, which then has to figure out where to put the message to, you can use this very powerful rules engine to send it now in this role to the protobuf decoder. This allows you to take weight off your backend, make full use of the rules engine, and optimize your routing because the message goes directly to the destination it's built for. So now we covered the device layer as well as the connectivity layer, and I'm handing over to the data geek, Mike, who's going to talk to you about the data abstraction layer. Thank you, everybody.
Thank you, Katja. Hi, everyone. Happy to be here and geek out about data. About a year ago, we started thinking very seriously about some of the biggest challenges with data. And as Katja already mentioned before, we have a few of large problems ahead of us, especially in the automotive and transportation industries. We have problems around data fragmentation, aka data that come in different formats, types, proprietary encodings of sorts, and so on. We have a tsunami of data coming up, yottabytes, as Katja estimated in 2030. And we have still ways to go before we can solve data delays, aka how do you synchronize a number of different signals in order to get to the right answer. So we started spinning our head around what's going on, how can we solve this problem? And the very first area that we found room for improvement was the traditional architectures that we see in the broader automotive industry today with ETL. Pretty much, I'm sure every one of you here has used in one way or another some form of data extraction, data transformation, data loading, like architecture. And this has served us well for many, many years and is starting to show its age. So we took a different stance, a different view, if you want, on what the future architectures around all this complex data that we are dealing about in the connected vehicle space should be served with. So we thought that instead of spending a little bit of time in data extraction, some time in transformation, and a ton of time in data loading and processing, what if we were to do some more pre-work in data modeling, then focus in data selection, and the last part, the data analytics, insights, and viewing, then becomes something that is as simple as pressing a button. So we thought hard about how we're going to make this transition, and we launched a service in preview at re:Invent about a year ago called AWS IoT Fleetwise that is a data abstraction layer to collect, transform, and transfer data from the vehicle to the cloud. So as Katya said, we are already using IoT device management, IoT Core, MQTT5 is wonderful and will empower a lot of scaled up use cases. And we build on top of that this model select view architecture. So what we do with the modeling side is that we create a set of APIs. We call them the IoT Fleetwise Designer APIs that, in essence, create an ontology, a semantic ontology of what is a car or a fleet of cars and what's like to be working with thousands or tens of thousands of signals that are slightly different ever so often between every car model out there. So that's the modeling part. The second part for the Fleetwise service is around data connection. And to connect, of course, we need an agent. And this is something that is open source, it's on GitHub. And we work with our partners and our customers in order to fine-tune that open source code to their end point, whether it's a tiny dongle, an automotive TCU, telecommunications unit, or an ADAS supercomputer sitting on a level 3 vehicle. So that's part two. Part three is when we select the data. And selecting the data is where we create certain data collection campaigns that describe what is of interest. As I said before, we can't keep on having an all-you-can-eat mindset. It just doesn't scale, and already many of you, I'm sure, are feeling the pains of what I call the big, bad data. So that's your friend here, the data selection APIs that we provide there. And now that you have done this pre-work, data modeling, data connection, and data selection, the rest of the pieces, data collection and data processing, storage, visualization, etc., becomes something much, much easier than before. So let's dive in a little bit more on what do we mean when it comes down to data modeling. So we started with standardizing and using something as commonly accepted as, you can think of it, a generalized format of sorts. And we picked something that happens to be used by many automakers already today, from our friends at the Covisa consortium. Covisa has proposed a format called the Vehicle Signal Specification, VSS, in order to create this representation of the vehicle. So when we talk about the vehicle, at the end of the day, we talk about a sum of parts. So a vehicle at the top level is a model of something that can have a body, a cabin, a chassis, general attributes like the VIN number, a powertrain, ADAS systems, and even the driver. So at the very top level of the tree, think of this as a tree, a vehicle has certain subsystems. Now, inside each and every one of these subsystems, there are further branches, attributes, aka metadata, and sensors and signals, aka the real data. So the VSS format now gives you this ability to start zooming down inside your vehicle. And in my example there, I extracted what is inside the powertrain subsystem. So in the powertrain subsystem, you will find in the VSS format today, also available on GitHub, right? Also available for any one of you to use, to extend, and to contribute back if you wish to. So inside the powertrain today, there are a few dozen of attributes. I picked a few of them just to give you this example. So inside powertrain, you can have branches around, is this a combustion engine? Is this a transmission? Is this an electric motor? Is this a battery? And you can go even further inside this tree. Inside battery, you can have a number of different attributes and branches like ID, capacity, charging, etc. And now inside even that layer, you can have all sorts of different measurements, like is the battery charging, discharging, or any other one of the values that you see there. At the end of the day, a signal example will be a fully qualified name that will read something like vehicle.powertrain.battery.charging.charge voltage, as one of the many, of course, examples there. Now, we have some sort of agreement, some sort of baseline of where to begin with when we talk about vehicle data modeling. Let's see then what we can do with that representation schema. For starters, our business as automakers or fleet managers of sorts is that we have a number of different vehicle models. We don't just make one car and one time only, we make multiple. So imagine that you have two vehicle models, as I have in the example over there, model M1, model M2. And for those of you that have worked in anything behind a vehicle, probably you know that you will have your own proprietary signals for that vehicle, also known as CAN-DBC, or VSpec, or many, many other proprietary formats. So what you have now is that internally, you have a number of different private signals that represent each and every of the systems and each and every of the vehicle models that you produce. Again, two layers, right? There is the systems that can be different, and then there is the complete vehicle models that are different. And again, all of those can be all over the place. You can have one model, you can have two, you can have 100 vehicle models. So now what Fleetwise does behind the scenes for you when you use the API is that it takes all of these inputs that you have. Let's say you have 10, 20 CAN database files. You have 100 Excel files. I have a key value pair somewhere. So we take these as inputs, and then we map them behind the scenes to the VSS global signal catalog. Does this remind you something? It's something very similar to private-public key cryptography. Think of your CAN-DBC. Think of the things that you know about your vehicles as private information you only know and you get to keep in your account, right? And then VSS becomes your public key that you want others to know in order to be able to communicate with you. For us, when we designed the APIs, we were thinking, what will make your life easier in order to merge and communicate, at the end of the day, data flows across your different vehicle models and types. So this is the superpower that, in some ways, this part of the vehicle modeling API can provide you. So now that you have these multiple vehicle models that have magically been mapped into a standardized language that can cut across all your vehicle models, so that when you're asking what's wrong with a tire, you don't need to worry about what is the exact name of the signal in one vehicle model versus the other, or what country is it at, or what metric he's using, or what range he's using, or what supplier has created this tire for one car versus the other. All of these are mapped eventually to the same entry in the VSS tree. So that's quite powerful. For those that have worked, again, with data, you understand that now I'm describing, in essence, a schema, an indexer of sorts that makes life easier while pre-processing the data. So now I have these multiple vehicle models. What I can do next is translate these multiple vehicle models into decoders of data. And here is how you can think of a vehicle decoder, a vehicle model decoder. It's an API that is translating each and every one of your in-vehicle proprietary signals into the model that you have created from your global VSS tree. Think of the global VSS tree as the dictionary of all languages in the world, and a vehicle decoder is that I'm going to only take English now and have this information being available in the vehicle to decode the proprietary signals. So the decoders are, in essence, very small configuration files that you can create, and you can create as many as you want, even in the same vehicle. The same vehicle can have multiple decoders for different purposes. You could be having a vehicle, by the way, that has different suppliers for the same system, right? As in my example, a vehicle can have a battery supplier A and a battery supplier B. What is even more challenging in data, you could be having different branches of the VSS tree that you have chosen to give you the same piece of information. In my example, the case here will be that you can ask the powertrain ECU for what is the status of my battery at any given second, but you can also ask the onboard diagnostics component of your car to do the same. So in some ways, what this decoder capability does for you is that it helps you make the best use of the actual intention of your campaign in order to collect your data. Vehicle decoders can be created and can be updated on demand, near real time, over MQTT. So now we have done the format, we have created the models, we have created the decoders. You can think of them again as the runtime translator between the public and the private keys that you can deploy all the time. The rest is literally the easy part. So the data collection now is, in essence, a set of APIs where you create a campaign. You can think of it as a set of programmable rules and deploy this campaign to a fleet of vehicles. You can select one, or you can select 1 million vehicles to deploy a data collection campaign. What does it look like? A campaign is, in essence, as you can see over there, a small snippet that defines the signals of interest and the rules behind their collection. Things that can be time-based, event-based, or complex logic-based. I like to think of our data collection campaigns, in essence, as small, maybe Kubernetes orchestration instructions, where instead of actually looking at how am I going to be deploying the software, you look at what are the data that I want to have in an enclave around the end-to-end use case of interest. So the data collection campaign enables end-to-end data management. You don't have anymore to be thinking, where is the CSV file that I can load, and where is the header so that I can understand what the heck is going on? With data collection campaigns, you have an agile, and in case I forgot to mention it, you can have thousands of these campaigns running at any given time in a single car, in a fleet of cars, or across all of your cars. So data collection campaigns become now your auto-scaling Swiss knife, where you can say, I want just this for now, or I want all of that later. So data collection campaigns do enable you to create these results all the way from the inception. So you wake up in the morning, you think about, what is my problem? I want to figure out whether there is a cell in batteries that may be having higher possibility of going out of range, of operational range, within the next 3 months, within the next 9 months. How am I going to solve that? You create a campaign. You create a programmable even campaign, where you can say, for these 100 cars over here, randomly sampled, give me smaller frequency data. But for these 5 cars over there, I want to know everything about that. And then you can do A/B testing. You can do anything you wish with the data that are coming in, because they are standardized, they are organized already for you. In reality, they look something like, next slide, like this on Amazon Timestream. You literally have the attributes that you actually prescribed in your data collection campaign coming in all the way to a time-based indexer, which is the Amazon Timestream database. And in there, you can fully prescribe, as I said, what is the schema that connects all the way back to the actual VSS fully qualified name that we started from. So finally, all this work that we did at the beginning is paying off, because now we have standardized names, programmable, accessible, fully qualified entities that you can run your analytics. And what you can do with that, it's completely up to you. One example is Grafana, the Amazon managed Grafana tool, where with no code, there is literally 0 code here, other than connecting Grafana to Timestream in order for you to be able to see dashboards, insights, and all kinds of other widgets therein. So we hope our customers will use some of our data abstraction capability for a number of cases. In my case, in my example around batteries, this can be faults, warnings, performance degradation, anomaly detection, and so on and so forth. I hope that I gave you a little bit of a teaser around what the data world looks like, but I do want to save the best for last. I want to invite Kevin for Mercedes to tell you more about some real-life lessons learned from our customer using AWS. Thank you.
Thanks, Mike, and good morning. So I'm Kevin, and I'm here to tell you about a project where we migrated our fleet of cars in Americas, and we at least will talk about the attempt in Europe. And that's the story I want to tell you of the Europe rollout. That is the second thing that we did. So I have a project that I'm going to talk about, but I really want to tell you this story. And it begins with our heroes on the Cloud Foundation team. They're in a Teams call in late summer. And they're talking with our colleagues about why we're making this change and about the rollout that we hope to do in late October 2022. So we have completed the rollout in the Americas, and we've gotten the benefits that we're looking for. I trust everyone in the audience's literacy, so I'm not going to read this slide to you. But one of our colleagues sums it up as 7 figures of cost reduction and hope for the future. That's what we're looking for here. We've tried explicitly to keep the scope of the current changes very, very small. We say a lot of, we're going to do surgery, and then we're going to do more. So when we talk about what are we actually changing, this is the scope of changes to the system. You can see on the left there the TCU, that's our telematics control unit. That's the component in the car that kind of functions as a modem. And that's the thing that communicates over MQTT. And actually, that's out of scope. The cars are not changing. That was part of the directives for our project. We want to make a very small change to a very large fleet of vehicles. What we call our vehicle anchor point in the previous system is what we're moving to IoT Core. So everything that the cars communicate to will communicate directly to AWS on IoT Core. And then we have some components that we use to communicate to the rest of the organization. We have you can think of it as the vehicles coming from the car go through the telematic protocol gateway there in the middle. Outbound messages go through the one that's named more expectedly, the outbound communication gateway, and then we have a connection monitor to tell the systems in our intelligent cloud whether you should try or whether you should use some sort of backup fashion. So our heroes are in the meeting, and they ask, how is the EMEA rollout going to go smoother than AMAP went? And without getting into too many of the details, the AMAP rollout was a little rough, and we had some rollbacks. We had some issues that we had to fix, and some of those are in the details of implementation. So looking here, kind of digging into that box, from IoT Core, when we get messages on topics, we send those through our Lambdas. This is primarily a stateless system, so you might be surprised to find databases on the diagram of the stateless system. We talked through that one of the things that the system needs to do is understand where to send a connection from a vehicle. There are internal systems for that, so we use DynamoDB and a DAX cache that has its own messages for caching. Every time a vehicle comes in, we need to do a lookup. We can't do that lookup dynamically, and by the way, this right side of the Lambda, that's a cloud boundary. There's another cloud provider who will not be named, is where we're communicating to on the other side of that. So we needed to do very efficient caching so that we don't add another back and forth on that for latency. To make this more concrete, what are we talking about in these messages? There's telematics data for sure, but the most concrete example that I can give you for thinking about what are these cars doing is remote starts and door lock and unlock. So when we're talking about what's our disruption to our customers, because we're driven by customers who drive, nobody says that but me, but I like it. That's what we're thinking about. So people can't use the expectations, they can't have that experience that we're trying to give them. So when we're talking about these disruptions, that's what the stakes are. So then the conversation for our heroes turns into, what are you tracking? And we bring up our single pane of glass. Mostly as a show, because our single pane of glass for the metrics for this system is a single pane. It's a single pane that's like 7 stories tall, and you'd need a skyscraper to project it on, but that's sort of the point. And some of the conversation here is about how the system functions and how we're measuring that. So the internals, you can see the lambdas there are interesting, and this is an interesting tie-in to what Katya said about MQTT5 and shared subscriptions, which we didn't have because we did this project over the last 1.5 years and rolled it out. Our release was in mid-October. We created lambdas for those outgoing messages. The previous system was using a JMS queue, so that was another approach when you don't have those shared subscriptions. And the JMS queue, if you're familiar with those, It has a mechanism for accepting a message, and then if there's some problem as you're communicating with the rest of the cloud, you can basically abort the transaction, and someone else will pick up that message. But in our mechanism that's making an HTTP call, if that HTTP call fails, whether it's on that line or something downstream of the box there, especially look at the TPG, we don't have a retry mechanism. So we put that into an SQS queue so that we can build our own retry mechanism on that side as a way to handle that prior to the introduction of shared subscriptions. All right, so there's a conversation about what is it that causes challenges before. We had some scaling challenges that we think are fixed, and the skeptical folks on the call with our heroes ask, well, you fixed it in AMAP. Are you sure that you fixed it in EMEA? And we say, yeah, we practice infrastructure as code. We've rolled out the same infrastructure configurations to both areas so that those scaling issues we're pretty darn confident that that's done. That's the benefit that we're looking for from that. Okay, some more questions. It's looking good for our heroes. Then they ask, how fast are you going to scale this up? Because in the Americas, we scaled up over the course of a week. We started at 1%, and 10%. And then as our confidence grew, we went up. And there was a couple cases where we came back and said, well, we think maybe there's a problem. You want to address things when there might be a problem rather than to definitely have an issue. And we said, yeah, we're gonna scale it from 0 to 100 in an hour. That's what we're going to do this time around. Our colleagues laugh. Our heroes don't. They're serious. That's the plan. 0 to 100 in 60 minutes, because one of the other quirks that we learned in doing this cutover is our ability, since we're not changing the car, our ability to change the vehicles between brokers is just with DNS. So when we go to 50% on DNS, that means it's a coin flip when the car reconnects which broker you connect to. Brokers are stateful systems. It doesn't behave very well if you send a message on one broker, get disconnected because you drove through a tunnel, and then reconnect to the other broker and look for that message. That was an artificial source of errors. So we think because we practice infrastructure as code, that we've addressed the issues that we've had before, and that will give us a cleaner data set. We spent a lot of time looking at things and saying, is it really? There's errors here, but are they really? And looking at those door unlocks. So what are the differences that we know? We went through our key metrics, and one fun detail here is the other kind of concrete end user metric that we tracked for the Americas and Pacific was remote starts. It was summertime, but people were still doing it, so that was nice. And while we were doing that, we said, well, as we look forward, what's the rate of remote starts that we're looking at in EMEA? And it's nearly 0. Anybody in the audience know why? Remote start's illegal in most of Europe. So that's not a metric that's going to translate from one to the other. But the rest of them still look good, and we have all of our metrics from both systems, from the previous broker and the current IoT Core in Datadog, so we can see them together. And we can see, here's the traffic from this week. It's always fun working in automotive where you have to say, do you mean traffic or do you mean traffic? Traffic. Which kind of traffic are we talking about? Because they scale together. And we can see, okay, this is what the scale is this week. This is what the scale is last week. It's not 1-to-1, but it looks pretty good. What's our tolerance there? All right. So the agreement, our heroes are on the call. This is late summertime. It looks good. We should roll out. We're on board with your crazy 0 to 100 in an hour. Let's do it. But we think that your team, my team, is based in Seattle. We think that you should really do this from Europe. You should come to the headquarters where most of the other systems that are in the cloud from the previous slide, they're in Germany. And so you should come here and do it from here so that we're able to have a fast turnaround and very little impact to our customers if something does happen. Okay. Not on the call, this guy named Kevin, who was on vacation. Great planning. I recommend that for all of your rollouts. And one of the teammates can't travel for happy reasons, being a new parent. So 4 of the heroes, Nation, Jeremy, Brian, and Torsten, book flights. They fly to Frankfurt, they drive down to Stuttgart, and they go to the heart of Benstown to do this cutover in mid-October. Whoops. So in mid-October, not very many weeks ago, in a conference room, we throw the switch. And it's not a switch, it's a console, keystrokes in a conference room. And at 1%, we check the error rate. It's low. It's not 0 because even at 1%, you get this broker ping-ponging. We ramp up, it looks good. It's looking good. The errors are not there. The account level throttles are not being hit, which is one of the other things that we checked before, that we'd gone through before. Our infrastructure of code is paid off. That downstream system is scaling up correctly, and we go to bed. We get woken up, but it's a false call because we have the thresholds really high. We go back to bed. A few days pass, everything is looking good, too good. Is it going to be okay? And then there's a realization. It looks like that some traffic is as we're looking at these rate of door unlocks, like I described, you get your curve over time. And of course, it's not exactly the same. From the previous week, traffic is different. We notice it certainly varies, and everybody has been saying that this is fine. But as we take a closer look into the details, we notice that this week's traffic has never exceeded last week's traffic. That means that there, we think, are some transactions missing or failing or not happening, because you should get that variance, the two scribbles as they go along, you should get that. So what's happening? And if it really is a problem, that means we would need to do a rollback. And at the point where we're seeing this, we've got about a day before our heroes need to get on their flight. So the question is, if we have to do a rollback, and the context for that rollback, right, is this whole thing worth it? Is 6-7 figures of cost savings and hope worth this kind of disruption to our customers, which we're very fiercely, advocates for? Have we gotten the surgery right? So we look at these downstream systems again. Is there some error rate? No, the error rates are not there. We're not seeing HTTP errors. Is it a problem as we're crossing the cloud? It's not. We're not seeing the timeouts. We have positive data there. We go back to certificates. Are we getting rejected at the front door? And a challenge for us, just in terms of transparency, is that the benefit that we want, we don't run anything on the front door. AWS handles this line from TCU to the green box totally without us. We don't have some sort of F5 networking appliance or something in there that we don't have to deal with. But that means that it's AWS's general infrastructure that's handling that certificate. And we don't really see the certificate errors if they were going to happen. Like, this is a thing that we wouldn't have visibility into because it's going to be full of, Russian hackers and all that kind of stuff that they're taking care of for us. That's the point. So we reach out to our teammates on the AWS side, and we say, we need to know, we've got to figure out if this is the problem, because if we don't find this, we've got to roll back, and we're running out of hours before our heroes have to get on the flight. So we turn on some additional logging. We get that work in, we get that widget enabled so that we can get that temporarily. There's no certificate failures. It's not a problem. It's within normal parameters. So what's the issue? Now we're really running out of time. And we remember that one aspect of that line involves your friend and mine IP whitelisting, which I have put into place and regretted so many times. Like, that would match, because we're not seeing errors. We've checked every line, and there's more that aren't on this slide, for some sort of error rate, some sort of message that's being sent incorrectly. We checked for if the cars are publishing on a topic, which you can see in between. Are they publishing on some sort of unexpected topic that's getting rejected for the security system that's making sure that I can't steal my cert out of the car and unlock yours with it? No, that's all working fine. IP whitelisting would explain it, but here's the skeptical part. Because when we talk to our other teammates, is it IP whitelisting? Because that would be not our fault. And that's wonderful news for us. So the first thing we need to do is we need to check to see if we have all of these blocks. What's the representation? We do the data mining through the system. We get that out of the logs and in Datadog. And we do discover that there is a block missing. There is a hole. When we graph the data that way, there is a hole, an IP-sized hole in the number of requests that are in the sort of distribution of IP addresses that are coming in. So now everybody's like blood runs cold, and there's 4 of our heroes huddling over the single laptop to see, did we request this block when we requested the IP whitelisting months ago? Because it's a very long lead process for the folks who are involved. Is the block in the email? That's where we're at. We've switched out of Datadog and our highest statistical analysis, and now we're Control F in Outlook. It's there. Okay, it's not our fault, but it still happened. We reach out to our partners. How quickly can you turn this around? Because it's Friday. The flight is at 6 p.m. in Frankfurt. We have to drive from, our heroes have to drive from Stuttgart area up to Frankfurt. Can you get this in? And what minute of this hour can you do it in? Like, that's the question. We get through to the right people. We've got the right escalations. They find the issue. They've got it in. Okay. But we have to get in the car. Literally, you have to get in the car. And we know that there is nothing in life guaranteeing you that you have one problem at a time. So we have to see this. And it's not instant. We don't get to see errors go away. We just have this squiggly line. Gets a little closer to the other squiggly line. It's going to take a couple of hours to even know. So our heroes get in the car, and they've got the laptop on the hotspot, and one person is driving in the back seat. And we're looking to see if these come together. Because if this really is the fix, then we have done a rollout in EMEA where we scaled up 0 to 60 in 60 minutes, or 0 to 100 in 60 minutes. And this will have been the only issue in the entire rollout. Halfway between Stuttgart and Frankfurt, there is a picture of 4 good friends stopped at a convenience store, and they all are holding paper bags. And there are smiles on all the faces as we've exceeded the previous week's numbers for the first time, and it's completed. And they fly home as conquering heroes. Being able to put this all together. So that's our story of doing the cutover. And we put it together. We did it through the Americas, and we have it in EMEA. And what we're looking for in the future is to be able to get a better view of this data as we go along, especially integrating better with our in-house tools. So we did these kinds of challenges through a lot of Datadog and by being the team that built it. So one of the takeaways for this is that if you're not us, this is really hard to do. It's really hard to figure out what's going wrong. And we get a lot of calls still in the Americas and Pacific of, oh, we think the hub is down. We think all the messages are broken. And we say, well, there are several million cars that are successfully communicating. Yours is not. Statistics suggest that the problem is not in the broker. And that's a clever thing to say. It doesn't make you very many friends because their side is like, well, great, but I still can't. It doesn't help me. You're correct, but not helpful. So where do we go from there? And being able to have much more of this integration and being able to do things to leveraging more of that pub-sub architecture, we think we can split that off into some debug streams and be able to give people much more a view of the traffic, and especially the traffic of just their cars. Almost no one should be able to see a live view of traffic for all cars, but if we can give you just your test car, that's going to be really powerful. The streaming architecture, especially looking at some of the MQTT5 aspects, are going to be powerful. And again, that pub-sub architecture in there is going to be really, really useful, as well as being closer to other Amazon tools like Kinesis and being able to do something with that where we didn't have that possibility on the other side. And if we choose to migrate more of the services that are on the far side of the cloud to this side of the cloud, that's going to be much more straightforward because that's, we've shown that we can get the data to the other side, and we've got it on this side. So that's our hope, and I think that's all for me. I'll hand this over to Mike.
So that's all, folks. Thank you for your time. If you have any questions, we're going to be standing right by the side of the stage for any follow-up topics you may have. If you want to see, by the way, some demos around IoT, Core, Fleetwise, and anything else, at CISA's forum, we have a number of kiosks that you can talk to some of the people there. Thank you again for your time. Hope you enjoyed the rest of the show.